In the previous example, we saw the thermal analysis of a gearbox housing. Now the second example that we will study is a thermal analysis on a heat sink. If you look at the problem description, the heat sink is subjected to a heat flux of 0.0118 watts per millimeter square, and there is a convection on all the other faces. You can see the surface on which the heat flow is acting, which is marked in the image over here. The material that we are going to use for the heat sink is aluminium alloy, and the convection on all the other faces is stagnant air correlation. Okay, so again in this case we will be using the convection data that is available in the Ansys Workbench software, and the ambient temperature that we will consider is atmospheric temperature, whatever is the default atmospheric temperature. Okay, so now let us perform this analysis in Ansys Workbench. We will come to the software. Again, this is a steady state thermal analysis. We need to add the material aluminium alloy. So I will take the aluminium alloy, return to the project, and now we have to import the geometry. Again, this geometry has been created using a CAD software. So let us import the geometry. We have the heatsink model over here. Let us enter into the geometry. Set the unit system, and now we will generate the model. So once you generate the model, you can see that the heat sink has been imported into the design modeler. Now if you have a look at the design very carefully, it is a symmetrical design. Can you see? If we consider the XY plane, about the XY plane also it is symmetrical, and about the YZ plane it is also symmetrical. So rather than taking the complete model, which will take a very long time for meshing and also solving, we can cut it into half. Like you can use the symmetry tool and take 1/4 of this design. For this, what we are going to do is, we will first see whether the planes are properly situated. So no, it is at this side. We need them at the center, right? So first we will have to understand what is the distance. So let us go to the new plane option. I'm taking it from the YZ plane, offset in the Z direction, and enter the values. You can see the displacement. Okay, it has to be, let us say, 75 more. Okay. So we have got it in the center. Now I will say generate. So there is one plane that we've got over here, and we need a similar plane over here in the center. So for that, I'm going to displace the XY plane. So again, the offset direction is in the Z direction. Okay. Now let us enter the values. In this case, it is 5. Okay. You can generate this. In this case, you can use your edge tool selection. Select any edge over here. It is 76, so half of 76. You can find out the value. So this value is not 35. So half of 76 would be 38. Okay. So now we have both the planes. So we will come to tools, symmetry option. I need to have the symmetry about 2 planes, and now select the planes. Plane 4 and plane 5, and generate. So this is the half model that we have generated. Okay. Now we will perform the analysis on this model, right? So symmetry has been done. We created the symmetry model. Now we will enter into the mechanical window. So once you come to the mechanical window, you will perform the analysis. So the geometry has been imported. We can see the geometry. I need to change my material to aluminium alloy. Okay. After this, we will mesh the model. You can also see the symmetry region that is available. So let us mesh the model first. I will use the default mesh settings. So with the default mesh settings, you have got quad meshing over here. You can use the relevance option to make it finer. Okay. Now once the meshing has been done, after this, now we will start applying the boundary conditions. Now the first thing that we need to see is the load acting on this face is a heat flux of 0.01188. Okay. Now it was on the entire face, but what we have done is we have cut the model into half. So we have taken 1/4 of this face. So what we are going to do over here is we will also divide this value of heat flux into 1/4. Okay. So for that you can use your calculator. 0.01188 divided by 4. So the heat flow that is going to act on the surface would be 0.00297 watts per millimeter square. Okay. So come back to the mechanical window, select your steady state thermal node, and we will apply a heat flux on this particular surface, and value of it is 0.00297. 0.00297 watts per millimeter square, right? After that, they have also mentioned that there is convection on all the other faces. So we need to select all the other faces for convection. So I'll take a convection tool from here, and I need to select all the other faces apart from this face. So I'll use my control key and start selecting all the faces. Make sure you don't select this face. Okay. There are small faces inside. You can select them all. You need this. After applying the convection, you can see if we have left out any other surface. Make sure you select all the faces so that we get correct results. So now we have selected all the faces. Okay, right. So I'll say apply. All the faces have been selected except the one on which you have applied the heat flux. Okay, now the surfaces have been selected. Now the temperature value of the atmosphere is not mentioned, so I will take it as the ambient temperature only, that is 22 degrees Celsius. And in film coefficient, I will again import the value and I will say it is stagnant air simplified case. Okay. Once that is done, then we will come to solution and we will solve the analysis. Okay. So now again I will take the temperature, maximum temperature. I'll take the heat flux, and now I will come to the probe option, and I will add one reaction. But let us first perform this, then we will understand what is the reaction option. So you can see the analysis has been done. Let us have a look at the temperature. So in this case, the maximum temperature induced in this heat sink because of the heat flow is 34.106 degrees Celsius. The total heat flux generated is 0.008911 watt per millimeter square. Okay, that is on all the other faces. Okay, now again for the heat flux, instead of the entire body, I can only select the area where I am interested. Okay, I only want to see what is the heat flux on this region, and I can solve. So you can see, you can use the probe option to select any area or any location to see what is the heat flux at that region. Okay, you can see the maximum and minimum probe also. After this, now we will see what is the reaction option. So when I click on reaction, you can understand what is the reaction on the body because of the convection. So when there is a convection happening, what is the reaction in the body? So now I can solve this. Now you will see that because of the convection, there is a heat loss of when you see a negative sign, that means the heat is getting lost. Okay, so it is 1.8509 watt. So that is the amount of heat that has been lost from the surfaces because of the convection. Okay, so this is how you will understand the different thermal quantities. You can also check the other quantities that are related to thermal analysis. Okay, fine. So this is how we will perform thermal analysis on the geometries, and these are the different types of results that we have understood or we have calculated. Okay.